Alright, we are going live. Give people a few minutes to come in. Uh, I've been fiddling around with the sound level coming out of my computer, and I've turned a lot of my fans down, and it got quieter. So I'm not sure. Or it got louder. So that's weird. I'm gonna fight with that some more. But my temperatures are still good, and I have all my fans at minimum. So that's it's weird that it got louder. All right. Um, Now I realize that some people might have issues getting to this particular live stream because a lot of you are running to the school to get your tests. Uh, so I'm just going to give it a second longer before I go through this. Uh, I'll probably go live again after I start the next one. Just to record some video for solving a circuit start to finish. That's not a thing that anybody needs to watch. I'm just going to do it to record the video. And, uh, yeah, I'll go live for it. And then, but that video is not going to go up immediately. I'm going to take some time and edit it and do some better uh, editing on those rather than just this live stuff. And that will hopefully do a pretty good job of explaining how to do a series circuit from start to finish. I will probably pull some from the homework and work those. Maybe not. I don't know how the copyright works with the homework stuff. And I don't want to like get in trouble for using a circuit that somebody else built. So I will probably I might work circuits similar to the homework so you can see, but I will use different numbers so that it's not exactly what the homework had. That's what we'll do. Uh, Probably I'll work 3 or 4 circuits. I'll see what it takes to do some timestamps. This is going to be my first edited video, so we'll see how that goes with the timestamps and stuff. Need a notepad and all that. Alright. When two batteries are connected as a series additive power source, they produce a voltage that is less than either of the batteries connected by itself. That's false. You put two batteries together in a way that they add together, they're going to add together, and you're going to get a higher voltage than either of the individuals. If you have two 1.5 volt batteries, you put them in together in additive, you get 3 volts. In a series circuit, the total or sum of all the voltages dropped across all of the circuit components is equal to the source voltage. That is true. So this is Kirchhoff's law. If you look up in your DC theory book, this book right here, if you look up in this book, you will see that Kirchhoff's law is basically this. Khan Academy has some very good videos about Kirchhoff's law that I usually play in class. I don't want to play them on YouTube because, again, copyright. Their videos are already up on YouTube. You can just go there. I will probably put those in the description of any edited videos I do. As current increases in a series circuit, the voltage dropped across each load in that circuit will increase. So, just by nature of the formulas, this formula right here, let's pull a circle out. Let's make it a little bit. Alright, just the nature of this formula. I don't like that. Just the nature of this right here. Sorry, I'm repeating myself. If you have a resistor that stays the same, let's say this is 100 ohms. If this is 5 amps, 100 times 5 is 500. If you were to increase this to 15 amps, well, that's going to increase the voltage. That's just how the things all work together as a group. You increase one thing, it's going to naturally increase the other things. Just like if you increase the voltage across a component, that's going to increase the amperage from that component. The only difference, and this can get a little bit confusing in like motors that have a output, like a power output, that uses this formula. I should just make these circles as a like clip art that I can just drop in. That's what I should do. I should really make the circle, save it, then I can just open up that file over and over. That's smart, whoever suggested that. So this is not my pen. So pi. If your power stays the same, so let's say you have a 1500 watt. Let's change it so it's not the same number. I'll change color too. Let's do 5,000 watt. No. 1250 watt motor. So this is a 1250 watt motor. It's always going to put out 1250 watts. It runs at 1250 watts. If you hook that motor up at 120 volts, well, your formula to find how much current it's going to pull is going to be 1250 divided by 120. And that will tell you how much current it will pull. But if you hook up that same motor at 240 volts, it's going to pull half as much current because the wattage output stayed the same. And wattage is just a function of voltage and current multiplied together. If you increase the voltage going to that motor, its output's going to be, or its current draw is going to be lower. And this would be a electric meter. Your electric meter reads wattage. So it doesn't really matter, like, if you hook up a 120 volt motor or a 240 volt motor, your electric meter cares about the the power draw of the motor. If you were to uh, the only savings you'll get is in the installation of the motor when you pull the wire, because you're going to want the higher voltage so you can run smaller wire, because the smaller wire is going to be able to support less current. And if you went higher voltage, you'll have less current draw, which means you have less power loss in the wire. And I've gone way above and beyond what the subject is for today in this little side rabbit chasing. Yeah. But that is something that you'll see out in the field is, well, these light fixtures are 30-watt light fixtures, but they can be hooked up 120 or 240. Which way do we want to hook them up? Yeah. In a circuit with two resistors in series. In a circuit with two resistors in series, the voltage dropped across the resistor with the larger resistance value will be less than the voltage dropped across the resistor with less resistance. So that is how it works. I mean, this is false. So it's the opposite of how it works. The larger resistance value will drop more voltage. And you can see this in a simple put the P too close. So if you have 50 ohms and 2 amps versus 10 ohms in the same amperage, because this is in the same circuit. 1 and 2, E1, E2. 50 ohms and 2 amps will give us 100 volts. Wow, that's going to come out to 120. And 50 ohms and 2 amps will give us 20 volts for a total of 120 volts. These numbers aren't true in this circuit that I'm drawing, just so nobody gets confused. All right. Now we got some circuits to work. Calculate the voltage that would be applied to a circuit connected with power sources as shown. So, the voltage here, if you look, you have 6 volts and 6 volts. They are pointed in the same direction. So the current flowing is going counterclockwise in both of these batteries. So your total is 12 volts. It's just a simple addition problem. And most people got it. Somebody didn't even know where to start, didn't know how to open their book and look. And that's going to be key with this stuff. And probably the people watching aren't the people who aren't opening the book. But since I can't be there all the time, you're going to have to open up your book and learn from the book a little bit. Do your homework, things like that. All right. In this particular one, let's open up a... Oh, that's Origin. I haven't opened that in 6 months, but it's still... Alright. Let's find that circuit. That's not it. Don't save. So let's enlarge. Let's make it 300%. Okay. And then let's create ourselves plenty of working space. Alright, so we have this circuit. And I'll just draw right on the picture. Are we red? No. Okay, so this battery is going this direction. Ooh, I have a... This battery is going... Oh. Delete. There's an up. That direction. This battery is going that direction. Let's override that. And then that battery is also going in that direction. So, now this is a racetrack, not a, like, these two batteries, the top and the bottom one, are not going in the same direction. And you might think that because they're pointed, you know, going from, the arrow's going from right to left. But what's actually going on, this is a racetrack around the lines. They're going opposite directions. So let's choose a direction. I'm going to say counterclockwise. Counterclockwise, and this is completely arbitrary. You can pick clockwise. But counterclockwise is going to be my correct direction. Let's go to pin. Let's do this. So anything going clockwise is incorrect, and everything going clockwise is correct. So, did I say that the same way twice? Counterclockwise is positive. So let's do, oop, that's not a pin. 1 second. Wise is negative. Alright, so this one going counterclockwise. It's positive. So we'll write, damn it, I keep swapping to a different 6 volts. Now we come here, 9 volts, it's going clockwise. That is negative. So 6 volts minus 9 volts. And you get to the next one, it's going counterclockwise. This is 30 volts. So we're going to do a plus 30 volts. You could start anywhere in the circuit, but I just started at the very, what I call the very first battery. 30 volts. And then 9 volts is going clockwise. So we're going to do another minus 9 volts. So what does that equal? You can plug it in your calculator and see. There we go. Let's drag this over so I can see both. 6 plus... wait. Clear. 6 minus 9 plus 30 minus 9. 18. 18 is our answer, and the answer of the questioning is... I don't know how any... Nobody got this one right. That's interesting. So a lot of these, I don't know how you could have possibly gotten. I think if you just added them all up, 6 plus 9 plus 30 plus 9, 54. So 54 is a reasonable wrong answer. I mean, you're still wrong, but I can see how you got there. 180, that's right out. 78. I don't know how you would get to 78 from these numbers. Do we have a 45? No 45. I don't know. I got nothing for how most of you did this. All right, moving along. We have a new circuit. Given the circuit and parameters shown, solve for the voltage drop on R1. This is the first question that I've presented to you. This is the first question I've presented to you to see. Or that you'll have. Sorry, I got a message that confused me. Okay, start over. This is the first question I've presented that you have to work the whole circuit. So let's do this one more time. I could probably do something with saving those. Let's see, that looks like the same. Yeah, that's it. Open with paint. Let's resize to, let's say, 400. Ooh, that's ugly. Oh well. Y'all can see the numbers good enough. Well, it's not white. That's weird. Alright, so let's work this one. So my recommendation when working a circuit is to make your chart. So let's make some lines so I can follow some lines. Let's make blue lines. So I have 2 components and 2 batteries. So I need 3 rows. 1, 2, and 3. And now I need I'm not going to bother typing. Ooh. R total, R1, R2. Let's do I total, I1, and I2, and green. E total, E1, and E2. Current flows from the negative terminal on a battery to the positive terminal on a battery. This is answering gravity's question, how do you know which direction it's going? Current flows from the negative to the positive. If you have multiple batteries like that previous question had, they're going in different directions, you just pick one that's like, yeah, this is the correct one. It's arbitrary. All that positive and negative says is a direction. So if you were to pick the wrong direction, all you're going to end up with is negative. Like in this one, if I picked the wrong direction, I'd have negative 12 volts as my voltage total instead of 12 volts. All right, so let's record our values. You see these batteries. Something I didn't tell you, on a battery, whenever it goes long, short, you have negative and positive. The short side is your negative side, and your long side is your positive side. So if they don't label it, that's what that's the sides. They have labeled it here. I don't know if they labeled it on the test. I didn't look. All right. So we have, and I don't put this part on the chart, but you have two batteries. They're both 6 volts each. And this is E of R1 and E of R2. Both batteries are 6 volts each. They are pointed in the same direction, so you will have 12 volts total. R1 is 250 ohms. And R2 is 10 ohms. So, since we've covered already in a previous lesson that resistance adds up to your total, you have 260 ohms total. Your goal, your first step in solving a circuit is to get two things on the same row. Currently, there are not, or before we added that up, there were no two things on the same row. And you couldn't solve anything to get two things on the same row. Now you have 12 volts and 260 ohms. Using the magic circle E over R times I, you can divide voltage by resistance, 12 divided by 260, and get 0.046. I'm going to stop there, 0.046. So that's 0.046 amps. Current stays the same throughout a series circuit. So current is equal, the whole column. So this will be 0.046 amps and 0.046 amps. Now that you have all of the ampacities, you have two things on all 3 rows. You can solve the rest of the row. The reason I haven't put power is because the question doesn't require you to get power, but all you would have to do is multiply across. So 0.46 times 12 would give you your final power, your power total. 250 and 0.46. Oh, was that 0.046? Yeah, it was 0.046. 11.5. And that will be your answer to the question that was asked. But let's continue. So this one would be 0.46, because 10 times 0.046 is 0.46. And to get your powers, all you have to do is multiply, because remember, going that direction, you multiply. Just on across. So let's see how you did. Oh, we got an 11.54. That's correct. Okay. Lots of people didn't know anything. That's a way to be. Find the unknown value V2. My doorbell's going to go off here in a second. They're dropping off some mail. Find the unknown value V2. So, We don't know what voltage 2 is. We do have voltage total, and we have all the individual voltages. I'm not going to bother. Y'all can visualize. So 12, and then 5 and 3. So 5 and 3 is 8 of your total 12 volts. So you're only missing 4 volts. And it looks like a lot of y'all worked that one out. Don't know how you got to 32. Alright, power delivered to a DC series circuit is the measure of the amount of work done. So that's what power is the amount of work done per a unit of time. So that's why kilowatt hours, that's how much power you consumed over the course of an hour. I say over the course of an hour. For an hour. It's a little bit more complex, but it's just giving the time portion of the power. Sum of the power dissipated by each resistor in a series circuit is equal to the... Oh my god, we've been streaming for that long? I'll finish. Total power. So all the powers add up. What would happen to a resistor if it was subjected to the voltages or currents which caused it to dissipate more power? It would be damaged. Yeah, so a resistor has like a volt or a wattage that it can dissipate, and if you put more power to it, it's going to damage it. Total power requirement in a series circuit. Yeah, so just you add up the powers, and that total power is the sum of the powers. How close are we? Yeah, we got some people watching. Find the total power dissipated in this circuit. So this is, you can use a formula, one of the 4 formulas that I gave you earlier. ERP would find this directly, or you can solve. So let's use the select tool. Okay, so ERP. Find the total power dissipated in the circuit. So you got 72 and 36. So that was 36 volts. That's a select brush. And 72 ohms. So you can use ERP. That's E squared RP. So 36 squared divided by resistance. That'll take you right to it. Or you can do 36 divided by 72 to get 0.5 amps. Now 0.5 times 36 to get 18 watts. So you can, there's easier ways than trying to remember all of the formulas. It's just up to you whether you want to remember the formulas or remember how to work through things. I would rather you know how to get through the circuit. So this is just asking for you to find the power for resistor R2. This is another one. You'll have to work the full circuit. I will do that in a live stream later just so we can get through with this one. And this one I do want to cover because I'm pretty sure something very similar to it is on the test. So you are given, and I'm just going to open up a new Oh, I can't use my pen to drag off the screen. Don't save. Make it twice as big. Give me some room to work. Alright. So we have our total, I total, and E total. The only one of these we know is E total is 9 volts. We have R1, don't know it. R2, or it's actually L2, isn't it? So it's... Let me try something. Huh, doesn't do anything. Okay. L1, we don't know the resistance value there either. I of R1, don't know it. I of R2, don't know it. E of R1, we're going to find that one like very soon. E of R2. So the question says we want it to be 4 volts. So we want E of R2 to be 4 volts. Now we have powers, power total, don't know it. Power R1, don't know it. Power R2. We do know that one. It is 0.5 watts. Let me erase this real quick. Okay, so since we know E of R2 is 4 volts and we have 9 volts total, we know we need 5 volts on this resistor. So that's our starting spot. Next, you want to look at the chart and see if you have any 2 things on any row. So you've got 0.5 and 4. 0.5 divided by 4 is going to be 0.125 amps. You can use your calculator. I did this yesterday. So 0.5 divided by 4 is 0.125 amps. And now, since we have amperage, this is a series circuit, so we know all the amperages. 0.125, 0.125. This circuit is specifically asking for the resistance. Yes, the resistance of R1. Well, now we have 2 things on the R1 row. We can solve the whole R1 row. But 5 divided by 0.125, I don't remember this one. I think it's 44. So 40 ohms is the answer here. All right. So that finishes this one. So let's get up that next quiz. Okay. Same story, different verse. Launch quiz, first year, DC Theory 2, 6 and 7. Alright. We have a new quiz up. Let the people know, since we were very late. I'll post it in the... Alright, and that ends the stream. You guys have a good this test, and I will see you guys at 3:45. Is it 3:45? Yeah, 3:45.